Hey everybody, so in this video we're going to define a couple of terms. We're going to look at ions, valence states, and oxidation states. So when we talk about ions, these are atoms that have a charge. So let's say we have the atom silica. It's very rare in nature that it would have a neutral charge, that it would have the same number of protons as electrons. Instead, it's very typical for silicon to have a +4 charge. So anything with a +4 charge we would refer to as a cation. So here we refer to this as a cation of silica. Now silica has 14 protons in its nucleus. So to get a +4 charge, that means it has to lose 4 electrons. It would have 14 electrons here in the neutral state, and then if we strip away 4 of those 14 electrons, leaving it with just 10 electrons, then it would have the 4+ state, allowing it to be then a cation, as we've discussed. And then there are elements that can take on electrons, like oxygen. So again, oxygen is very rarely ever in the neutral state. Oxygen has 8 protons in its nucleus, as we've discussed in other videos. It has to be 8, otherwise it's not oxygen, just like silicon has to have 14 protons, otherwise it's not silicon. But the number of electrons is variable, and if an oxygen atom has 8 electrons, then it will be neutral, but usually only it has 10 electrons, giving it a 2- charge. And anything with a negative charge is referred to as an anion. So a cation is anything, any atom with a positive charge, and an anion is anything with a negative charge. And so we've just given 2 examples, but there are many others. So for example, sodium is commonly in the 1+ state. That would be a cation. Right. And then fluorine, very commonly in the with a -1 charge. So that qualifies as an anion. Now, we have other ways of talking about the very same thing. This term valence is very common. We talk about so-called valence states or valence electrons. The valence electrons, I'll just write an E- for electrons. These are the electrons that are in the outermost shells that are available for bonding. Available for bonding. And we come back to our example of silicon, 4+. When it was in the neutral state, it had 4 electrons that are available for bonding. How does it acquire this 4+ state? It's going to bond with, let's say, 2 oxygens. Remember, oxygen commonly has a 2- charge. So if we have 2 oxygens, those 2 oxygens in total are willing to grab up 4 electrons, and they're happy to take them from silicon. And so we can have this unit here, quartz, and that would be neutral. So the valence electrons then for oxygen and silicon are the 2 additional electrons here in oxygen and those 4 electrons that are being shared with oxygen on the silicon side to create this neutral compound SiO2, otherwise known as the mineral quartz. So we could talk about this 4+ as being the valence state, and then we could talk about oxygen 2-. The 2- charge is the valence state of oxygen. Now, another aspect of this valence stuff is that in geology we often talk about oxidation state. So this is just the last term that we'll discuss here in this video. The oxidation states of elements are, again, they're really kind of synonymous with what we refer to as the valence state. The reason we talk about oxidation states is that oxygen is the single most abundant atom in the entire Earth. It's more abundant than silicon, it's more abundant than iron, Well, it might not be more abundant than iron, but they're going to be pretty close in abundance. There might not be enough oxygen in Earth to, for example, oxidize all of Earth's core. But in any case, in Earth's crust and mantle, oxygen definitely is the most abundant element, and it's the most abundant anion. And so, because of that abundance, of all the other kinds of anions that are moving about and that cations can bond with, oxygen is the most likely one to be grabbing up electrons. Now, silicon can lose those 4 electrons to other kinds of compounds, but more than likely it's going to bump into an oxygen atom, and so it's oxygen that's going to be grabbing up those 4 electrons from silicon. So we talk about oxidation states, and the oxidation state of silicon, in other words, the number of electrons that oxygen can pull away from silicon would be 4. But there are elements like iron that have multiple oxidation states. So iron can be 2 plus, or it can be 3 plus. And so when we talk about oxidation states, it's usually in reference to these kinds of elements that have multiple oxidation states, because that's where it becomes really interesting. So silicon is always 4 plus. There's really not a lot to discuss in terms of its environment. We almost always find it in the 4 plus state. There are some rare cases when you can find it a little bit more reduced. But with oxygen in Earth's crust, we can find it in either one of these 2 states. Even in the same mineral, it can be in both of these states, both the 2 plus and 3 plus, occupying different sites in a crystal structure and satisfying different charge balance requirements in different parts of the crystalline structure. And so there it becomes really important to know whether or not iron is acting in a way that it's giving away 2 electrons or 3. And so we talk about these so-called oxidation states because, in a sense, they're really telling us how much oxygen is around. If there's a lot of oxygen around, then most iron is going to be 3 plus. Whereas if there's not very much oxygen around, it's going to be 2 plus. If there's no oxygen around, then oxygen can have a neutral state. So for metallic iron, we would have iron just bonded to itself with no net charge. So in these kinds of elements, and iron is just one of the more prominent examples, we have varying valence states, otherwise in geology typically known as oxidation states.